Hi students, this is Jen Hawksworth, and in this video we're going to review derivatives and integrals from Calculus 1. So we're basically going to do a set of practice problems. Our first problem will be to take the derivative of a function, and the function we're working with is f of x equals 6, the fourth root of x plus 2 over x plus 5x. So sometimes before you take a derivative, it helps to rewrite the function. So the first term I'm going to rewrite as 6 times x to the 1/4 power. Anytime we see roots, go ahead and write them as exponents. And then the second term, I'm going to go ahead and bring the x that's in the denominator up into the numerator so we're able to use the power rule when we take the derivative. And that last term, just keep it as this. So when we take the derivative, we're going to write f prime of x, and this is going to equal 6. And then when I'm taking the derivative of this first term, I'm going to use power rule, so I'm bringing down the 1/4 of the x, and then I have to subtract 1 from the exponent. So 1/4 minus 1 is going to give me -3/4. That's the new exponent on x. Then I'm going to do the same thing with the second term, use power rule. So I have the 2, and then I have to bring down the exponent, -1. And then I'm going to have to subtract 1 from this exponent. So -1 minus 1 is going to give me -2. That's the new exponent. And then this last term, anytime we see x to the first, whatever you're multiplying to the x, in this case 5, that's what stays, the x goes away. And then I'm just going to rewrite this one more time to make it look a little neater. So 6 times 1/4, I'm going to write that as 3/2. If you want, you can keep, I'm okay if you have negative exponents. If you want to leave that, that's fine. And then I'm going to rewrite the 2 times -1 as just -2. And just copy down the 5. So this is fine. If you want to rewrite this one more time to get rid of the negative exponents, you can. That's whatever your preference is. So you can rewrite that way as well. All right, so that's the first problem. All right, so now we're going to try another derivative problem. So this is number 2, and our function is going to be g of x equals 3x squared sine x plus 4. Okay, so I'm going to take the derivative, g prime of x, and in this one, I have a product in the first term, so I'm going to have to use the product rule when I take the derivative. I'm going to call this u and this v. So the product rule is going to be u times v prime plus u prime times v. So I'm going to keep the u part, the 3x squared, and I'm going to take the derivative of the v part, which in this case is sine x, the derivative of sine, cosine. I'm going to add the derivative of the u part, so u is 3x squared. So when I take the derivative of this, it's going to be 6x to the first. And then I keep the v part, which is the sine x. And then this last term, just a constant. Anytime we take the derivative of a constant, that's just going to be 0. All right, so your final answer, just 3x squared cosine x plus 6x sine x. And just leave it like that. That's number 2. All right, for number 3, we have h of x equals x squared minus 5 over 3x plus 2. I'm going to take the derivative of this. Write down that, use that correct notation, h prime of x. And for this one, I've got a quotient, so I'm going to have to use quotient rule. So this part here, the numerator, I'm going to call u, and the denominator is going to be v. So the quotient rule, as a reminder, it's going to be v times u prime minus u times v prime. That's going to be the numerator. And in the denominator, you're going to have v squared. Okay. So I'm going to do the denominator first. I'm just going to have 3x plus 2 squared. So whatever the v is from the function, the 3x plus 2, you're going to just square it. In the numerator, you're going to keep the v part, which is the denominator. So I'm going to have the 3x plus 2, and then I need a derivative of the u part. So if I look up here, the derivative of the numerator is going to be 2x minus 0. Then you have your negative. Then you're going to keep the u part here. Make sure you put parentheses around it. And then the derivative of v. So the derivative of this here is just 3. And then clean this up. We don't want to have it left like this. So in the numerator, I'm going to go ahead and I'm going to take this here and distribute it through to the terms. I'm going to do the same thing with the 3 and also with this negative. So just use your algebra skills to rewrite the numerator. So this is going to give me 6x squared plus 4x. That's for the first term. And then I'm going to take the negative and this 3 and distribute them both through to the x squared minus 5 in the parentheses there. So I'm going to have negative 3x squared plus 15. For the denominator, you have 3x plus 2 squared. Just leave it like that. Don't try to FOIL it. That'll just make it a little messier than it needs to be. So I'm going to keep the denominator, leave that as it is in the final answer. The only thing I'm going to do is just clean up the numerator one more time because we do have some like terms. So this is going to become 3x squared plus 4x plus 15. All right, and then just leave it like that. That is fine as a final answer. All right, now we'll try number 4. So here we have y equals 3, 4 minus 5x to the 5 6 power. All right, so I'm going to go ahead and find the derivative. Now for this, you have to use a chain rule, because you have a composition function. You have the inside function, which is the 4 minus 5x, and you have an outside function, which is that outside exponent of 5 6. So you're going to have to use chain rule. Chain rule tells us we're going to take the derivative of the outside first, keep the inside, chain on the derivative of the inside. This 3 here is a constant multiple. That's just going to stay here. All right, so I'm going to take the derivative of the outside function first. So the outside function is that 5 6 exponent. So you're going to bring down the power like you normally do. You keep the inside, subtract 1 from the exponent. So 5 6 minus 1 is going to give us negative 1 6. So I've taken the derivative now of the outside, and now I want to take the derivative of the inside function. So I'm looking at this, and I'm going to chain it on, basically just multiply it to the back. So derivative of 4 minus 5x is just going to be negative 5. And then don't leave it like this. We could clean this up. All right, so we have this here that I can think of as 2 in the denominator, or 1/2. And then I have the 5 here and the negative 5 that I can multiply together. So I'm going to clean that up. 5 and negative 5 is going to give me the negative 25 in the numerator. This 3 6 gives me a 2 in the denominator. And then if I want this exponent to be positive, I'll just go ahead and take that and put it into the denominator. So that's my final answer there. That's the derivative. All right, so for number 5, this one's going to be a little bit more involved. Not the derivative itself isn't that bad, but I have this problem here because I want us to review some algebraic skills. So it's the algebra that's going to be actually the harder part when we do this problem. So we want to take the derivative. We have s of t equals 3t times the square root of 1 minus t squared. So the first thing I'm going to do, because I see a root there, I'm going to go ahead and rewrite the root as a exponent. So square root is a 1/2 power. Now, after I've rewritten it, I'm ready to go ahead and take the derivative. So I'm going to go ahead and label that s prime of t. And then like we saw in a previous problem, we're going to have to use the chain rule, the product rule, because you have a product here. This can be the u. This part can be solved as the v. But also when we go and look at the v here, when we take the derivative of v, we will have to use the chain rule too. So we have to make use of both the product rule and the chain rule for this problem. There's a couple rules going on in here. All right, so when I do the product rule, I'm going to keep u times the derivative of v. I'm going to add on derivative of u times v. All right, so for u, that's just 3t. And then when I take the derivative of v using the chain rule, that means I have to do the derivative of the outside first. The outside is that 1/2 power. So I'll bring that exponent down. I keep the inside, subtract 1 from that exponent. So 1/2 minus 1 is -1/2. And then I have to chain on the derivative of the inside. So the derivative of 1 minus t squared, which is -2t. So this part right here, this is all the derivative of v. Then we have to do another term for that product rule. And the derivative of u, which is, u is 3t, so the derivative of 3t is just 3. And then we copy down our v, the v factor. All right, so technically we've taken the derivative. I don't want to keep it like this, though. It's a little messy, and we can clean this up using some algebraic skills to write this so it looks a lot neater. So that's what I'm going to do now, and this is just to kind of review some of our algebraic skills. So this first term, I have this 1/2, and I have this -2, right? So the 2's are going to divide out. I'm going to be left with a negative in the numerator. I also have this 3, so the 3 is going to be left in the numerator. And then I have a t here and a t here, so I'm going to have a t squared. That's all I have in the numerator. This part here, the 1 minus t squared to the -1/2, I'm going to go ahead and put that into the denominator so it has a positive exponent. So that's already looking a lot nicer. That's that first term. The second term, I'm just going to leave that alone for now. I'm not going to do anything with that, so just copy that down. Now, you see how in the parentheses you have the 1 plus t squared? Oh, that should be a negative, right? That's a minus. Let me fix that. Okay. So I have a 1 minus t squared, and then over here I have the same parentheses, the 1 minus t squared. I have two terms. I'm going to go ahead and rewrite this so that I can put these two terms together. So what I'm going to do is I'm going to take the second term and multiply the top and bottom, the numerator and the denominator, by the denominator over here in this first term so that they have common denominators. And things should clean up because we do have that 1 minus t squared in both the terms, right? There's some commonality there. So first term, again, I'm just going to copy that down. And then the second term, I now have a 1 minus t squared to the positive 1/2 in the denominator. And then I want to clean up this part here. See how that you have the same base? So all I'm going to do is add the exponents. Well, 1/2 plus 1/2 is just 1. So all I have to write down is that base to the first power. All right, so it's already looking a lot nicer. And now that they have the same denominator, I can go ahead and put them together and write this as one single term, one single fraction. So I'll just write the two numerators across, combine those, and then just a couple more steps and we're almost done. I'm going to go ahead and take this 3 here, distribute that through. So I have -3t squared plus 3 minus 3t squared. And don't do anything, don't worry about the denominator, I'm just going to copy that back down. And then the last step, now that we have some common terms, we can combine, namely this one and this one. In the numerator, I'm going to go ahead and do that. So I'm going to have 3 minus 6t squared. And now if you want to leave the denominator as it is, you can, or since it is a 1/2 power, if you want to go ahead and put it back into square root form, you can. So this is the final answer. So the actual derivatives, the derivative rules, the product rule, chain rule, weren't that bad. It's actually the algebra afterward that can get a little messy. So just keep your algebra skills sharp by doing these practice problems. All right, so now we're going to try number 6. So here we have y equals 2e to the 3x squared plus 5x. So in this one, when we take the derivative, since we have an exponential function, that e there raised to an exponent to a power, we're going to have to use the rule for the exponent rule for derivatives. So for this one, we're going to look at the exponent on the e, and we're going to have to find the derivative of the exponent, and then we actually end up writing it in the front here. Now we do have this 2, that's fine, that's a constant multiple, just bring that down. And then here's where the derivative of the exponent is going to go. So the derivative of 3x squared is going to be 6x. The derivative of 5x is just going to be 5. So this part here that I just put down in the parentheses, that is the derivative of the exponent. And then your exponential rule for derivatives tells you whatever exponent function you had in there, exponential function you had in there, you just go ahead and copy that down. So this part here, e to the exponent, that just stays in the derivative. And then you could leave it like this is fine. Or if you feel inclined to go ahead and take that 2 and multiply that through, you could also do that. So either of these answers is fine. That's number 6. That wasn't so bad. Okay, number 7. Here we have f of x equals ln of sine x. So here we're going to have to use derivative rule for logs. You have a log rule for derivatives. We're going to write f prime of x. And the log rule tells us that when we take the derivative of natural log, the log goes away and you're going to have a quotient. Whatever is inside the log, in this case the sine x, you're going to take that and put it into the denominator for this quotient. And you're going to find its derivative and put it in the numerator. So the derivative of sine is cosine, and that's what I'm going to put in the numerator. So we've taken the derivative, that's the derivative. We want to rewrite this and get this a little neater though. Cosine of sine is, cosine over sine is cotangent x. So I'm just going to write that instead because that looks a little nearer than having a fraction. And that's the final answer. Okay, so number 8, we have g of x equals e to the 3x tangent 2x. All right, so this one we might recognize again as a product rule because you have 2 factors. Each of those factors has the variable in it. So we're going to have to use the product rule. And then we have an exponential function, so we're also going to have to use the exponential rule. And we have a tangent in there, so we're going to have to know what the derivative of tangent is, one of those trig functions. All right, so just going to write the rule under here. So it's going to be u times v prime plus u prime times v. That's the product rule. I like to write out the product rule and quotient rules so I have kind of a guide in front of me. So I'm going to keep u, which is the e to the 3x, and then I need the derivative of tangent 2x. Right? So the derivative of tangent is secant squared. I leave a little space here on purpose. We'll go back and fill that in. So derivative of tangent is secant squared. Now here, because you don't just have an x inside of the tangent function, you have a 2x, you actually have to use a chain rule too. So we have to chain on the derivative of the inside function. So you're taking the derivative of the outside function first, which is tangent, right? That's the outside function. The inside function is the 2x. Derivative of the outside, secant squared, keep the inside 2x, and then chain on the derivative of the inside. The derivative of the inside is just 2, right? That's the derivative of 2x. I'm just going to put that in the front though. So we're actually using several rules to do this the derivative of this function. That's the first term. And then the second term, you take the derivative of e to the 3x first. So you keep the exponential function. You look at its derivative, look at its exponent, 3x. Find the derivative of the exponent, which is 3, multiply that to the front. And then I'm keeping the v part, which is the tangent, 2x. Just going to write this a little nicer. All right, 2 e to the 3x secant squared 2x plus 3 e to the 3x tangent 2x. And that's fine. You can leave it like that. If you wanted to factor out the exponential function, you can, but I'm just going to leave it as it is. So that's number 8. So for number 9, we have y equals ln the square root of x squared plus 3x. So we know that when we do the derivative of a natural log, the log goes away, you're going to have a quotient. Whatever is inside the log, the square root part, is going to go into the denominator of the derivative, and then you would need to find its derivative and put that in the numerator. Well, the derivative of the square root of x squared plus 3x, you would have to rewrite this square root so it's a 1/2 power. You would have to use chain rule because you have an inside and outside function. And it's not that you can't do it, but there might be an easier way to take this derivative. So instead of just trying to take the derivative, looking at the function I have, I'm going to try to rewrite the function first and then take the derivative. So I'm going to rewrite the square root as a 1/2 power, and then I'm going to put on the side here some rules. So you had different rules for logs. There is the power rule. So if you have ln a to the r, you could write that as r ln a. Not a derivative, just a power rule for logs. You also had product rule. So if you have ln a times b, you could write that as ln a plus ln b. And you had quotient rule. So if you had ln of a over b, you could write that as ln a minus ln b. So sometimes rewriting a natural log function will make taking the derivative a little easier. So for example, this last one that I put down here, the quotient rule, right? If you instead of taking the derivative of this and having to use the quotient rule because of the quotient being inside of the log, if you rewrite it first, then you would just take the derivative of each term separately, and then it will eliminate having to do the quotient rule. So for the problem I'm doing, number 9, I'm going to use the power rule to rewrite the log so that when I take the derivative, I don't have to worry about doing the chain rule. So I'm going to rewrite the function first, and then I'm going to take the derivative. So now instead of having a 1/2 as an exponent and having to do chain rule, I just have a 1/2 as a scalar multiple, which is easier to work with. All right, so I'll bring down the 1/2, and then when I take the derivative of the natural log, I have to, whoops, that should be an x. Whatever's inside the log, I put that in the denominator, and then its derivative goes in the numerator. So the derivative of x squared plus 3x is 2x plus 3. And I'm just going to rewrite this one more time. Take that 2 and distribute that through. And that's my final answer. So just keep that in mind. Sometimes if the derivative looks a little challenging, see if you can rewrite the function. All right, so for number 10, we have y equals secant 2x plus 1 cubed. So we're going to have to use chain rule because we have an inside function and an outside function. So we'll have to use that, and we'll also have to know the derivative for secant. All right, so I'm going to write y prime of x. I'm going to take the derivative of the outside function first, which is that something being cubed. So I'm going to take the exponent, write that in the front, keep the inside, subtract 1 from the exponent, so now it's squared. and then you chain on the derivative of the inside. Now the derivative of the inside, let's call this is the inside, let's call that something. I'm just going to call that W. When I take the derivative of secant, I actually have to use the chain rule again. So I'm actually using the chain rule twice in this problem because secant, it's secant of 2x plus 1. So secant's the outside, the 2x plus 1's the inside. So I take the derivative of the outside first. So the derivative of secant is secant tangent, and then you would have to chain on the derivative of the inside. Inside is that 2x plus 1, so the derivative of that inside would be 2. Let's multiply that to the back. All right, so that's going to have to all come over here. I'm going to write the 2 first. Secant 2x plus 1, tangent 2x plus 1. All right, so sometimes it might help if you do a little scratch work on the side. I'm going to erase this. Done with that. And then I'm going to rewrite this one more time. So we have 3, 2, I'm going to write that as secant. I have 6, I'm going to write that as 6. And then I have secant here, squared. I have a secant here. So this is going to be secant 2x plus 1, but I want to cube it since I have 3 factors of it. And then I've got tangent 2x plus 1 in the back. And then just leave it like that. All right, now we have number 11. So we have h of x equals x minus 1 over x plus 1 squared. So here we're going to have to use chain rule and quotient rule. So I'm going to write h prime of x equals, I'm going to do the chain rule first. The inside function is that quotient. The outside function is something squared. So I'm doing the outside function first, derivative of the outside. Bring down the exponent then. Keep the inside, subtract 1 from the exponent, and then we're going to chain on the derivative of the inside. And this is where we're going to have to use quotient rule. All right, so for quotient rule, this part's going to be u. This part's going to be v. So it's going to be v times u prime minus v prime times u over v squared. That's like my guide there. So I'm going to have a quotient. Whatever's in the denominator, you're just going to copy that down and square it. So I'm going to have an x plus 1 squared. In the numerator, I'm going to keep the v part, the denominator, so the x plus 1. Chain on the derivative of u. U is the x minus 1, so its derivative is just 1. We're going to subtract. Take the derivative of v now, which is just 1. Keep u, which is the numerator, x minus 1. And then we've taken the derivative, and now we're just going to clean this up a little bit. Okay, so the numerator here, the part, let me circle it. This part here, I'm going to clean this up. That is going to give us just x plus 1 minus 1x minus x plus 1. There we go. All right, so it looks like we have 2, x minus 1, and then this part is just 2, right? The x's cancel. And then we have x plus 1 cubed in the numerator now, right? Because I had 1 factor over here, 2 over here. And I'm just going to put the 2's together, right? That's a 4. And if you want, you can also distribute that 4 through if you wanted to. I'm just going to leave it like that. So that's the derivative. All right, now we have number 12. This is the last of our derivative problems. So we have y equals e to the x times ln x. So we're going to have to use our product rule that we've seen a couple times now. This is u, this is v, so the derivative is going to be u times v prime plus u prime times v. Let's write that down. So I have y prime equals e to the x. The derivative of ln x is just going to be 1 over x, right? Whatever's inside of the log x, you put in the denominator. Its derivative, 1, you put in the numerator. And then the derivative of e to the x is just e to the x. And then we keep the v part, which is ln x. And that's it. You can just going to rewrite this first term, but that's all there is to this problem. So that's our last derivative problem. Now we're going to go over some integration practice problems. All right, so for number 13, we want to find this integral here, basically find the antiderivative. But before I can do that, I'm going to have to rewrite this a little bit. The first term, I'm going to write that cube root as a 1/3 power. And in the second term, I'm going to bring the x cubed up into numerator. That way I'll be able to use power rule in those first two terms. And you know what? We're going to have to rewrite this first term one more time. So we have x to the first times x to the 1/3. So the base x is the same, right? I want to put those together by adding the exponents. So 1 plus 1/3, I've got x to the 4/3 power. And then I'm just going to copy these second two terms down. Now we're ready, after a little bit of rewriting, we're actually ready to find the antiderivative. So for the first term, we're going to use power rule. Right? So we're going to add 1 to the exponent. So 4/3 plus 1 is going to give us 7/3. And then we can divide by that number. Do the same thing for the second term. I have 2, which is a constant multiple, just bring that down. I'm going to have x to the, add 1 to the exponent, so -2, divide by that number. And then here I just have 4. Whenever you have a constant and you're integrating it, just multiply on whatever variable you're integrating with respect to. And then I'm just going to add on plus c, your constant of integration. I'm just going to do a little bit of rewriting to make this a little nicer. So instead of dividing by 7/3, I'm going to multiply by the reciprocal, 3/7. And in the second term, the 2's divide out. I'm just going to put the negative like in front. Oh, also, if I want to put the x to the -2 back into the denominator, you can. So that can be a 1/x². And then just leave these other two terms as they are. And that's the antiderivative. All right, so for number 14, we have the integral, it's x plus 4 squared dx. So this is like x plus 4 times x plus 4, right? So you have a product in there, and there's no product rule for integration. So you're going to have to actually FOIL this to get x² plus 8x plus 16 dx before you can actually integrate. Then you just integrate each term separately now that it's just a sum of terms. So the first term, we're going to use power rule, so you add 1 to the exponent, divide by that number. Do the same thing for the second term, add 1 to the exponent, divide by that number. And then for this third term, you have 16, a constant, so you just multiply the variable to it, and then you have plus c, your constant of integration. And I'm just going to clean this up. I'm going to write this second term as 4x². And kind of leave the other ones alone. So that's the antiderivative for number 14. All right, so for 15, we have sine x over cosine squared x dx. So can't take the derivative or find the antiderivative of this as it is. There's no way to integrate it. So again, we're going to have to do a little rewriting. So you should be comfortable enough with your trig identities that you can rewrite them until you get them to a place where you can actually integrate. I'm just going to break up, I have a cosine squared in the denominator, so I'm just going to split that up a little bit. Still have my dx in the back. And then this part here, sine over cosine, that's just tangent x. And then 1 over cosine I can rewrite as secant x, and then you have your dx in the back. So you actually have a rule for when you see secant tangent and you want to integrate that, that's just going to be secant, right? The derivative of secant is secant tangent. We saw that earlier when we were doing one of the problems for derivatives. So be comfortable with your trig identities and know how to rewrite them if you have to, so that if you can't integrate as it is, when you rewrite it, you can get it to a place where you can actually integrate. All right, so for 16, we have 4 e to the 4x plus 7 dx. I'm going to use substitution for this one. So we're gonna let u be equal to the exponent, the 4x plus 7, and then du is going to be equal to 4 dx. All right, so there's the 4, there's the dx. So that's going to come out and get replaced with du. So 4 dx, that's your du. I'll put that in the back. And then this is what we set u equal to. So that is going to be our new exponent u. Okay, so after we've done the u substitution, we've converted the whole integral into 1 in terms of u. And the idea of u substitution is to take an integral we can't integrate yet and to convert it into something that's easier for us to integrate. So now when I want to find the antiderivative e to u, that's just e to u plus your constant. And then just make sure you back substitute. So plug back in what u is equal to, in this case 4x plus 7. So that's your antiderivative. Okay, number 17, we have secant 5x dx. Again, here I'm going to do a little u substitution. So we have a composition function. We have secant the outside, and we have 5x as the inside. So if you have a composition function, you can try to set u equal to the inside. That's a general rule of thumb. And then the du is going to be 5 dx. All right, well, you have your dx in there, but you're missing that 5. So we're going to fix it. So if I want to just multiply the inside by a 5, just put a 5 there, so now I have the 5x. I'm allowed to do that as long as I divide somewhere by 5. So if I'm multiplying somewhere by 5, then I divide somewhere by 5 so that I don't change the value of the integral. So basically I have 1/5 times 5, I've multiplied by 1 essentially. And then after I fix that constant multiple, then I'm ready to go ahead and do the substitution. So the 5x gets replaced with u, and the 5 dx gets replaced with du. Right? Those are our substitutions. So I have the 1/5, and then the antiderivative for secant is the natural log ln of secant u plus tangent u. That's another one of those trig integrals that you should have memorized. Plus c, or constant of integration. And then the last thing I'm going to do, since we started out with the integral in terms of x, I need an answer in terms of x. So just remember at the end to back substitute. So secant 5x plus tangent 5x should be inside of the natural log. So that's the final answer. Okay, so for 18, we have 5 over 6x plus 7 dx. And again, I'm going to use some u substitution. So when you have a quotient, you can try setting u equal to the denominator. So then the derivative du is going to be equal to 6 dx. All right, again, we're missing a 6, but we can fix that. All right, so I'm allowed to multiply the inside by a 6. Right, I want a 6 dx, so now I have it. As long as I divide somewhere by a 6. Right, I have the 1/6, and I have the 6, so I've just multiplied by 6, essentially. And then I'm ready to do the substitution. So I have 5/6 integral. I'll just put 1 in the numerator as a placeholder because I like to put the du, the differential, off to the side. And I'll put a u in the denominator. All right, so that's what it looks like after we substituted over. So we have our 5/6, and then the antiderivative of 1 over u, that is going to be ln of u. And then just remember to plug back in what u was. So in this case, 6x plus 7. So our final answer is 5/6 ln of 6x plus 7 plus your constant of integration. All right, so for number 19, we have x square root x plus 3 dx. So we're going to use some substitution here. I do have a composition function. I have the square root. So the outside is the square root, the inside is the x plus 3. So I'm going to set u equal to the inside of that composition function. And then du is just going to be equal to dx. Okay, so now I'm going to have the square root of u, and dx is equal to du, so I'm just going to switch that over. And then here's where I have a problem. I can't have an x in there. I have to, when I convert it over to an integral in terms of u, I can't have any x's left over. So I have to have x in terms of u, and that's okay. We can do that. So this x is going to get replaced using this substitution that we set up. So since I have an x by itself over here, I'm going to get this x by itself. So x is equal to u minus 3. So that's what's going to go right here, u minus 3. Make sure you put parentheses around it. Now we've converted to an integral in terms of u. And I still have to do a little rewriting, right? Every time we see a root, go ahead and write that as an exponent. And then I have a product, which there's no product rule for integration, so we're going to have to take this u to the 1/2 and distribute that through. All right, now we have a difference of terms, and we can integrate the terms separately. So we need to do a U-substitution. We also need to rewrite this before we can actually integrate. All right, so when I find the antiderivative for that first term, I'm using power rule. So I have to add 1 to the exponent. That's going to give me 5/2. Instead of dividing by 5/2, I'm going to multiply by the reciprocal, 2/5. Do the same thing over here. Add 1 to that exponent. So I get 3/2. Instead of dividing by 3/2, multiply by the reciprocal, plus our constant of integration. And then I'm going to just clean this up a little bit more. Plug back in what u is equal to. Here, this 3's divide out. Okay. Now here we've integrated. We have our answer in terms of x. You can leave it like that. I'm just going to go a little further, just so we can review some algebra. But if you gave me this final line here on the test or something, I wouldn't take any points off. But I do want to show you how you can clean this up a little bit more. So you see how you can factor out a 2. That's going to come out. And you see how you can factor out an x plus 3 to the 3/2. Take that out too. And then actually I'm going to factor out a 1/5 also. So I can get rid of the fraction in that first term there. So when I factor all that stuff out of those two terms, what do I have left over in this first term? After all that comes out, I'm going to have just an x plus 3 left over to the first. And then the second term, this term here, what do I have left over when I factor all of this out? Just a 5. And I didn't leave enough room, so I'm going to have a plus c there. All right, so that's what you get when you factor that out. If this doesn't look familiar, then you want to review some of your algebraic skills. And then I'm just going to clean this up just a little bit further. This part in here, that's going to be x minus 2. All right, so that's another way you can give the final answer. But like I said, if you give me this line here as a final answer, that is completely acceptable. If you're familiar, remember your algebraic skills, you can go a little bit further and write it this way if you want to. All right, so for number 20, we have 1 over square root x, 1 plus square root x dx. So this is in our U-substitution problem. So sometimes it's a little bit easier to figure out what the u should be depending on the problem. So if you have a composition function, like a function has an inside and outside, it's good to set u equal to the inside. If you have an exponential function like e to some exponent, you can set u equal to the exponent. If you have a quotient, right, a numerator denominator, you can try to set u equal to the denominator. So those are like the rules of sum you would have been given back in Calc 1, but sometimes you don't really apply directly, so it does take a little bit of trial and error in some cases. So if you pick something out for u and you find your du and you get stuck and it doesn't work, then try to go back and see if there's something else you could pick out for u. In this case, I'm going to let u be equal to the 1 plus square root x, or 1 plus x to the 1/2. And then du is going to be equal to 1/2 x to the negative 1/2 dx, or 1 over 2 square root x dx. Okay, I'm going to rewrite a little bit in here. This square root x, I'm just going to kind of move it over here next to the dx so that I can see all of this right here is almost here. It's just, you're just missing that 2. But that's okay, because we've seen before that we can fix a constant multiple. So I'm just going to go ahead and divide by 2, as long as I multiply by 2. Okay, so I'm multiplying the numerator and the denominator by a 2. So I'm fixing that constant multiple. Then I'm ready for substitution. So all of this is going to get replaced with du. And that gets replaced with u because that's what we set up for our substitution. So it's a substitution problem. It's a little bit different than the ones we've done in this session already. All right, so then I can go ahead and integrate. 1 over u is ln u, and then just back substitute. So I have 2 ln 1 plus square root x plus c. So that's the final answer. All right, 21, we have e to the 4x times sine e to the 4x dx. And again, we're going to use substitution for this. Now, this one's a little bit easier, I think, because you do have a composition function right here. Sine is the outside function. E to the 4x is the inside function. So set u equal to the inside function, e to the 4x. And then du is going to be equal to 4 e to the 4x dx. Just going to rearrange this a little bit. And then I'm going to multiply the inside by a 4. Right, so now all this will come out and get replaced with du. And if I multiply the inside by a 4, I have to divide somewhere by a 4. So I'll put a 1/4 on the outside there. And then we're ready to do our substitution. So I have the 1/4 integral sine u, and then all this is just du. So I'm just integrating sine u. So I have the 1/4. The antiderivative for sine is negative cosine. So I'll put the negative here, cosine u plus c. So I have negative 1/4 cosine e to the 4x, right? That's what the u is equal to, plus c. So that's my antiderivative right there. All right, for number 22, we have e to the 2x plus 1 over 5 minus e to the 2x plus 1 dx. I have a quotient, so if I use substitution, I'm going to try to set u equal to the denominator, which is the 5 minus e to the 2x plus 1. So then du is going to be equal to negative 2 e to the 2x plus 1 dx, which I almost have in there. So I'm going to go ahead and fix that just off by that negative 2. So I'm going to multiply the inside by negative 2 as long as I divide somewhere by a negative 2. Then I'm ready to do a substitution. So I have negative 1/2 on the inside, outside there. And then all of this, it gets replaced with just a du, which I'm going to put off to the side. So I'll just put a 1 in the numerator like a placeholder. And then this part here, the denominator is what we said was going to be equal to u. So I'm going to put a u in the denominator. So I have just the negative 1/2, and I'm integrating 1 over u, which I've seen before. That's just ln u plus c. And then we just have to make sure we go ahead and back substitute. So I have negative 1/2 ln 5 minus e to the 2x plus 1 plus c. So that's the final answer for that one. All right, and the last few problems that we're going to do in this review are going to be the definite integrals. We want to evaluate definite integrals. So the first set of problems we did in this review were derivatives, and then we evaluated we found indefinite integrals, and now we're evaluating definite integrals. All right, so now the last few problems we're going to do for this review are evaluating definite integrals. So in the first part of this review, we did derivatives, then we found indefinite integrals, and now we're evaluating definite integrals. All right, so like before, sometimes you have to rewrite before you can actually find an antiderivative, right? So I'm going to rewrite that square root as a 1/2 power. Then I'm going to go ahead and integrate each of these terms. So add 1 to the exponent, so I'm going to have x to the 3/2 power. Instead of dividing by 3/2, I'll multiply by the reciprocal, 2/3. Second term, add 1 to the power to get 3, also divide by that number. And then 4 is a constant, so just multiply by the variable. And then we're integrating from 1 to 4. So we're going to go ahead and plug in the upper limit of integration, 4 first. So that's going to give us, that's 4, and then plug in the 4 here. Clean that up in the next step. This is 3, and I'm plugging in 4. Okay, and then plugging in 4. Then we're going to subtract, plug in the lower limit of integration, which is 1. Okay, and then clean this up. This is 32. You can plug this into your calculator. Plus 192 minus 16, and then we're subtracting 4 plus 3 minus 4. That should have been a negative, right? I copied that wrong. And then the final answer should be, well, let's see, we have 208 minus 3. Your final answer is 205. All right, so for the definite integrals, you should be getting finite numbers. All right, for number 24, we have the definite integral going from 2 to 4. 4 2x minus 5 cubed dx. That's a cube. Okay, so since we have a composition function, an inside and outside, and the inside being the 2x minus 5 and the outside being that third power, we're going to use U-substitution. So I'm going to let u be the inside of the composition function, and then du is going to be 2 dx. So here's my dx, right? And I have a 4 here. So I'm going to take that 4 and write that as 2 times 2, because I want to put a factor of 2 as the dx. That way I can do the substitution. So this 2 just comes down. The inside here we said was going to be equal to u. And then this is getting replaced with du. Now, these limits of integration, the 2 and the 4 there, those are x values. So when we convert over to an integral in terms of u, I need those limits of integration to be u values. So when x equals 4, right, that's the upper limit here, then u is going to be equal to, just use this here, 2 times 4 minus 5, or 3. And when x equals, what was the lower limit, 2? Then u is equal to 2 times 2 minus 5 equals negative 1. right? So these numbers here then, the -1 and the 3, those become your new limits of integration. So now we're integrating really from -1 to 3. Those are the u values for integral in terms of u. All right, so then you use your power rule to integrate. So you add 1 to the exponent, divide by that number, and we're going from -1 to 3. So I have 1/2, I plug 3 in, minus I plug -1 in, and then I clean this up. And I messed up. Should be a 1 here. All right, so you get 40 as your final answer. All right, so for 25, we're going from 0 to 9, and I've got x plus 3 over square root x dx. So I can't integrate this as it is because I have a quotient in there. And don't try to do like U-sub unless you need to. See if you can rewrite the function without U-substitution. So what I'm going to do is I'm going to take the terms in the numerator, divide them both separately by that one term that's in the denominator, the square root x. Just rewrite those roots so that they're 1/2 powers. And clean this up. So I have negative, oops, that should be a positive 1/2. I have x to the 1/2 power plus 3x to the negative 1/2 power dx. All right, so then I'm just going to come up here using the power rule. I'm going to add 1 to that exponent. 1/2 plus 1 is 3/2. Instead of dividing by 3/2, I multiply by its reciprocal, 2/3. I'm going to add the 3, add 1 to this exponent, so I have a 1/2 power. And instead of dividing by 1/2, I'll multiply by the reciprocal, 2 over 1. And then we're going from 0 to 9. Okay, so I have 2/3, 9 to the 3/2 power, plus 6, 9 to the 1/2 power, and I'm subtracting, and then I would plug 0 in, but that's just going to be 0, so I don't have to worry about that. And then just plug this into your calculator to clean this up. This is just going to be 36 as your final answer. All right, so that brings us to number 26. This is our last review problem. So it's an indefinite integral. We're going from 0 to pi over 4, and we have secant x dx. So the antiderivative of secant x is ln secant x plus tangent x. And then we're going from 0 to pi over 4. All right, so I'm going to go ahead and plug in pi over 4. I'm going to subtract, and then I'm going to plug in 0. All right, then I'm just going to clean this up a little bit. So ln secant pi over 4, what's that? Let's go over here, put a little note here. If I want to find secant pi over 4, and maybe I'm not familiar with secant, I can rewrite this as 1 over cosine, which I should be more familiar with. So cosine pi over 4 is square root 2 over 2. Okay, so then this, when you simplify it, that's just going to be square root 2. Think of taking this denominator, multiplying by the reciprocal, and then when you rationalize this 2, this is 2, you get square root 2. I'm just going to put that on the side into here. So I have square root 2 plus tangent of pi over 4. Do a note for that too. If we're not as familiar with tangent, think of that as sine over cosine. Well, sine of pi over 4 is square root 2 over 2. Cosine pi over 4 is also square root 2 over 2. So this is just 1. So I just have 1 here. And then you can do similar reasoning for secant and tangent of 0. and that you're going to end up having ln of 1 plus 0, but ln of 1 is just 0, so the final answer is going to be the ln of square root 2 plus 1. That's the final answer. All right, so that's it for the review problems. Make sure you spend some time going over them. Review all the formulas for derivatives, integrals. Be familiar with your definite integrals as well. The more you remember from your Calc 1, the better off you're going to be in this Calc 2 course. Thanks for listening.